Hi guys, welcome back. So in this video we're going to see chapter 4, Introduction to Buffer Overflows. So the previous chapter, the chapter 1 got 4 videos, chapter 2 got 3 videos, and chapter 3 got 2 videos. So if you guys missed this or previous videos, please go and watch to get better understand. So before you guys continue this video, so let's go for the topic now. Introduction to Buffer Overflow. So in this video, we will present the principle behind a buffer overflow, which is a type of memory corruption vulnerabilities. We will explore how program memory is used, how a buffer overflow occurs, and how the overflows can be used to control the execution flow of an application. It is vital that we have a good understanding of the conditions that make buffer overflow attack possible in order to develop an exploit to take advantage of the type of vulnerabilities. Introduction to the x86 architecture. To understand how memory corruptions occurs and how they can be leveraged into unauthorized access, we need to discuss program memory, understand how software works at the CPU level, and outline a few basic definitions. Program memory. When a binary application is executed, it allocates memory in a very specific way within the memory boundaries used by modern computers. This figure shows how process memory is allocated in Windows between the lowest memory address and the highest memory address used by applications. Although there are several memory areas outlined in the figure, for our purpose we'll solely focus on stack. Okay, the stack. When a thread is running, it executes code from within the program image or from various DLLs loaded by the applications. The thread requires a short-term data area for function, local variable, and program control informations. This data area is known as the stack. To facilitate independent execution of multiple threads, each thread in a running application has its own stack. So stack memory is viewed by the CPU as a last in, first out structure. So this essentially means that while accessing the stack, item pushed on the top of the stack are popped off first. The x86 architecture implements dedicated push and pop assembly instructions in order to add data or remove it from the stack. Function return mechanics. When code within a thread calls a function, it must know when address to return to once the function completes. So this return address along with the function parameter and local variable is stored on the stack. This collection of data is associated when one function call and is stored in the section of stack memory known as stack frame. When a function ends, the return address is taken from the stack and used to restore the execution flow back to the main program or the calling function. While this describes the progress at a high level, we must understand more about how this is actually accomplished at the CPU level. So this requires a discussion about CPU registers. Okay, so CPU registers. CPU registers to perform efficient code executions. The CPU maintains and uses a series of 9 32-bit registers. Registers are small, extremely high-speed CPU storage locations where data can be efficiently read or manipulated. The registers names were established for 16-bit architectures and were then extended with the advent of 32-bit platform. Hence the letter E in the registers acronym. Each register may contain a 32-bit value or may contain a 16-bit or 18-bit value in the respective sub-register as shown in the example picture. So for the EAX registers, since the purpose of the video is to demonstrate a buffer overflow, we will not delve into the details of the assembly, but will highlight some of the elements that are important to our specific discussions. General purpose registers. Several registers are often used as general purpose registers. To store temporary data, there's much more to these discussions, but the primary registers for our purpose are EAX. So as you guys can see here, so EAX, which is the accumulate and is used for arithmetical and logical instructions. So EBX is a base pointer for memory addresses. ECX. So ECX is a count register which is used as a loop, shift and rotation counter. And then EDX. So EDX used for IO port addressing, input output port addressing, multiplications and divisions. Okay. And then ESP. ESP, the stack pointer, keeps track of the most recently referenced locations on the stack by storing a pointer to it. A pointer is a reference to an address or locations in memory. When we say a register stores a pointer or point to an address, the essential means that the register is storing the target address. Since the stack is in constant flux during the execution of thread, it can become difficult for a function to locate its own stack frame, which stores the required argument, local variable and the return address. So next, EBP. So EBP, the base pointer, solves this by storing a pointer to the top of the stack when a function is called. By accessing EBP, a function can easily reference information from its own stack frame via offset while executing. Next is EDI. EDI, which is the destination index, used as a pointer addressing the destination memory buffer in string copy operation. And the last one is ESI. ESI, which the source index, used as a pointer addressing the data source as a string copy operation. Buffer overflow walkthrough. In these sections, we will analyze a simple vulnerable applications that doesn't perform proper sanitizations of users' input. We will analyze the application source code and discover that by passing a specifically crafted argument, we will be able to copy our controlled input string to smaller size stack. Buffer overflow walkthrough. In these sections, we will analyze a simple vulnerable applications that doesn't perform proper sanitizations of users' input. We will analyze the application source codes and discover that by passing a specifically crafted arguments, we will be able to copy our controlled input string to a smaller sized stack buffer, eventually overflowing its limits. This overflow will corrupt data on the stack, finally leading to a return address override and complete control over the EAP register. Gaining control of EAP is the first step in creating a successful buffer overflow in the module. In this video, we will focus on controlling EAP, and in further video we will explain how to leverage this into arbitrary code executions. This is some very basic C source code for an application vulnerable to a buffer overflow. Even without knowledge of C, the logic of this program is fairly easy to understand. First of all, it is worth noting that is C, you guys can see here. So this main function is treated the same as every other function. It can receive arguments, returns value, etc. The only difference is that is called by the operating system itself when the process starts. So in this case, the main function first define a character array named buffer. So as you guys can see here, so that can fit up to 64 bits, 64 characters, since the variable is defined within a function. The C compiler will treat it as a local variable and will reverse space for it on the stack. Memory function, specifically this memory space will be reserved within the main function stack frame during the executions when the program runs. So then the program proceed to copy the content of the given command line argument into the buffer character array. Note that the C language doesn't natively support string as a data type. At a low level, a string is a sequence of characters terminated by a null character, or put it another way, a one-dimensional array of characters. Finally, the program terminates its executions and returns a 0 to the operating system, which is the standard exit code for success. When we call this program, we will pass command line argument to it. The main function process this argument with the help of two parameters. One is argc and then argv, which represent the number of arguments passed to the program and an array of pointer to the argument strings themselves respectively. Introducing the immunity debugger. So we can use an application called a debugger to assist with the exploit development process. A debugger acts as a proxy between the applications and the CPU, and it allows us to stop the execution flow at any point to inspect the content of the registers as well as the process memory space. While running an application through a debugger, we can also execute assembly instructions one at a time. To better understand the detailed flow of the code, although there are many debuggers available, we will use Immunity Debugger, which has a relatively simple interface and allow us to use Python script to automate tasks. We can attempt to overflow the buffer in our vulnerable test application and use Immunity Debugger to better understand what exactly happened of each stage of the program execution. Okay. So to execute the program, vulnerable program, so we will open in the dialog. We select string copy.exe, which is the compiled version of the source code we analyzed earlier. So prior to clicking open, we will add 12A characters to the argument field. These 12 characters we will serve as the command line argument to the program and will subsequently be used by the string copy functions. When the debugger launches the application, the execution flow of the program will be paused at entry point. Unfortunately, in the example, the entry point doesn't coincide with the beginning of the main function. Okay. This is not uncommon, as often the entry point is set by the compiler to a section of code created to help prepare the execution of the program. Among other things, the preparations include setting up all the arguments that main may expect. Before going further, let's become more familiar with Immunity and practice navigating the most relevant features. That main feature is split into 4 windows or panes. So the upper left window shows the assemble instructions that make up the application, and then the highlighted instruction in blue sub ESP0C is the assemble instructions to be executed next, and it is locations in the process memory space is displayed in the leftmost column. So these upper right windows contains all the registries including the two we are most interested in, ESP and EAP. So since by definition EAP points to the next code instruction to be executed, it is set to the address of the instruction highlighted in the assemble window. So the lower right window shows the stack, and then lower right window shows the stack, and it contains the view contains 4 column a memory address, the hex data residing at the address, an ASCII representation of the data, and a dynamic commentary that provides additional information related to particular stack entry when available. So the data itself in the second column is displayed as a 32-bit value called a dword, displays as 4 hexadecimal bytes. Note that the address at the top of the pan is identical to the value of stored in ESP in the registry windows. So and then final window in the lower left shows the content of the memory at any given address. Similar to the stack window, it shows 3 columns including the memory address, and then hex and ASCII and representations of the data. As the name suggestion, the window can be helpful while searching for or analyzing specific value in the progress memory space, and it can show in different format. So I can just right click and change it. Okay, it's time to navigate the assembly code. When loaded, the application execution was halted at the program entry point as indicating by the word paused. Okay, so you guys can also use this shortcut key F7 F8 is a step into and step over. So as you guys can see here, the difference between the two is that step into will follow the execution flow into a given function call, while step over will execute the entire function and return from it. Okay, since the entry point in this case doesn't coincide with the beginning of the main function, our first goal is to find where the main function is located in memory. To do this, we can search the process memory space for the error message that was included in the program source code. So to search, we can just right click on the program. We right click inside the disassemble window and select search for all reference text strings. So the result window clearly shows that string were yes, there you go, strings where we are looking for. Okay, just double click okay on that. Okay, when we double click the error message, we return to the disassemble window, but this time inside the main function. As you guys can see here, depending on your screen resolutions, you may need to scroll down in the disassemble window to find the highlighted instructions. Okay, so you guys can see we have managed to find the error message. So what we're going to do is we can just set the breakpoint on it. So a breakpoint is essentially an intentional pause that can be set by the debugger on any program instruction. To set a breakpoint on string copy function calls, so as you guys can see here, so we can just press F2. As you guys can see here, the blue highlight. So once you press the F2 shortcut, so the breakpoint will placed here, so on the instruction. So next we can continue the execution flow by selecting run from the debug menu or by pressing F9 shortcut. So almost immediately the execution stops again just before the call to the string copy functions, where we can set our breakpoint at address 004015AA. So EAP is set to this address as well, since it is point to the next instruction to be executed in the stack window, as you guys can see. So we find the 12A characters from our command line input, okay, and the address 64-bit, or by pressing F7. Notice that the address in the upper left assembled instructions window have changed because we are now inside the string copy functions. Now we can just double click the A string. So once we double click on the string, copy the destination address in the stack pan to better monitor the memory write operation occurring at the address. So this change the view of the stack pans slightly. Now we can see relatively positive and negative offset. First, note the offset 0, now highlight and noted with the arrow indicator, is addressing 0065 FE70. So this is the beginning of the destination buffer where our input string of as will ultimately be copied. Since we define a 64-byte buffer in our program, our buffer extends from offset 0 to offset +4. 0 including the null terminator for our character array. Okay. Notice that there are what appears to be written address in the buffer as well as various other oddities. Since we didn't initialize or clear our buffer when we define it, that space is filled with residual data which the debugger attempts to interpret when the time comes to copy our array of as to buffer. This residual data will be overwritten. So next, notice the return address of 004015 at the top of the stack. So this is the address we will return to the when the string copy has completed and correlated to the move EAX0 instructions immediately following the call to string copy that brought us here. That call instruction pushed this address on the stack automatically for us. At this point, we can let the execution continue to the end of the string copy function by selecting executing till return to return from the debug menu, or just pressing Ctrl F9 shortcut button. Okay, so this will allow us to see the result of the functions. So our 12A characters have been copied to the stack into the buffer, and we are clearly within the 64-byte buffer limit imposed by the declared local buffer variable size. Before proceeding, make a mental note of the address located at the offset 4C from the buffer variable. This is the main function return address. The address of the instruction will return to once the main function has completed its execution. So we will see this in action in a moment. Now that this string copy function has completed its execution and all data has been copied into destination buffer. So it is time to return the execution to main through the return assemble instruction. So these instructions pop up the value of the top of the stack into EAP registry instructions, the CPU. Okay, to execute the code at that locations, next if we single step through these return instructions within F7, so we arrive back the main function's address as expected. So since the next address after the string copy call, the next instructions move EAX0 is the equivalent of the return O in our original source code, and sends the exit status 0. So it is time to return the execution to main through the RETN or return assemble instructions. So these instructions pop up the value at the top of the stack into the EAP registers the instructions, the CPU, to execute the code at the location next. Okay, so if we single step through these return instructions with the pressing F7, So we arrive back at the main function address as expected. Okay, so since this is the next address after the string copy call, the next instructions move EAX 0. So as you guys can see here, so is the equivalent of the return 0 in our original source code and send the exit status 0 to operating system at the moment. So we reach the main functions, we'll simply return the execution to the very first piece of the code created by the compiler. Okay, then the return assemble instructions pop up the main function's return address from the top of the stack and execute the code there. We must linger at the point a while longer to understand the bigger picture. In the case there are no boundary checks on the size of the copy in our C code. Therefore, if we pass a longer string as an input to our program, enough data will be returned to the stack, and eventually we should be able to overwrite the return address of the main parent functions located offset for C program from the buffer variable. Okay, so this means that if the return address override is performed correctly, the instruction pointer will end up under our control, as it will contain some of our argument data when the main function return to the parent. Overflowing the buffer. In the previous example, we only wrote 12 bytes out of the available 64. So the program ran and exited clearly as expected. However, the offset between the buffer address and the main function return address is 76 bytes, which is equal to 4C in hex. So if we supply 80 A's as an argument, they should all be copied onto the stack and write post the bounds of the assigned buffer into the target return address. So to do this, we can reopen the application from the menu and enter 80 A's for the argument. Now let's find the string copy function again. Okay, so all string. Since Immunity Debugger serves breakpoint across different debugging sessions, our breakpoint is still set on the call to string copy. We will press F9 to run the program until the breakpoint is hit. We will hit our breakpoint, so we will step into the string copy functions with F7, as you guys can see here. Then we will execute up to the return instructions with Control F9. So if we continue the execution with F7 and proceed to the return instruction in the main function, the overwritten return address part of our string of as we will be popped up into EIP. So as you guys can see here, that EIP is a 414141. So at this point, the CPU tries to read the next instructions from address 414141. So the hex representations of our string of A's. So since this is not a valid address in the process memory space, the CPU triggers an access violating, which crashes the applications. Once again, it is important to keep in mind that the EIP register is used by the CPU to direct code execution at the assemble level. Therefore, obtaining reliable control of EIP would allow us to execute any assembly code we want, even shell code, to obtain a reverse shell in the context of the vulnerable application. So that's it guys for this video. So in this video we have completed the introduction to buffer overflow. So next video we will see fuzzing, okay, and some more topics. Is very interesting topics. Okay, please subscribe my channel Press the bell button to get more update. Share the video to your friends guys. See you, bye bye.